Hello Pantherae and welcome to my new video, and today I will show you the derivation of a resonance curve using complex numbers. What do I mean with the resonance curve? Suppose that you have a spring and in the end of the spring is attached some mass or something with a mass m, and the spring constant of the spring is m. Let's suppose that there is a gravitational force mg pulling down on the object which is attached at the end of the spring, and there are plenty other forces. For example, the force of the spring, which is proportional to displacement from initial position of a spring, unreleased spring. So that means that unreleased spring has this neutral position over there, and there is some displacement by this force, which I will call x0. So the force is x0 plus y, and y is the displacement from this new position. So this is y, a new displacement from this position. So the bob is moving up and down, and there should be we will describe this motion using complex numbers. So let us first analyze the circular motion, harmonic motion first. Analysis of harmonic motion. So let us write over there analysis of harmonic motion. Let us suppose that something, it can be a bob or attached on the spring, or it can be a pendulum. The end of the pendulum in first approximation is moving up and down, and this motion we will describe by a function cosine, because this motion is periodic, and this is called harmonic motion. This is the displacement y from the initial position or from the equilibrium position, and this length is called an amplitude, because the amplitude is the largest distance which the bob is moving up and down. Yes, so this is up and down from this initial position, and it can be described by function cosine. So this y is a times cosine, and there is angular frequency omega times t. And angular frequency, let us recall that angular frequency is 2 pi times the regular frequency, which is afterwards 1 over t, and t is the period of the motion. So this distance is 1 period. So now let us reformulate this motion using complex numbers. So what do I mean with that? You can imagine that this motion, which is cosine, is just a projection. I will rotate this axis 90 degrees to the right. So it's just a projection of circular motion on the y-axis. So you can imagine there is some bob rotating around this in this fashion, or if I rotate it, this should be the direction of motion, and there is some point on the edge of this circle moving with angular velocity. This is circular motion, well described with the first year of study at high school, or I think the most 15 or 16 years old will understand circular motion and what comes with it. So like what is velocity in this motion, and so on. Interestingly, we can describe it not just using vectors, because this is just projection. Yes, when the bob is here, the projection is here, and the motion, which is periodic in this fashion and regular with the same velocity, will produce this harmonic motion. I will write here some diagram what I am doing now, what I will do. When you have some function, some function y, and you have just the just first coordinate of this motion, and you add the second coordinate, and you are trying to find velocity of this motion, and it's hard to find it, so it's maybe easier to find velocity of this this motion, which is composed of two independent motions, and then find velocity 1, velocity 2, and then just forgot this v2 velocity. This is very easy example of which is called abstraction in math, and it's used everywhere, I think. This is just one example. This motion, which is in this fashion, I will produce by projection of this point, which is moving in this direction, and the velocity of this point is very easily found. It's just this vector, and the projection of this vector, this vector has to be the velocity in x direction, or not x direction. This should be called y1, but I will call it just y for simplicity. So this is v. What is the acceleration and when the motion is circular and periodic regular? You may know that the acceleration is in the direction of the center, and it has the magnitude of omega squared and times y, which is, I should call it this point y, this distance, or r, and this is omega times y. Where do the complex number came in? I think this point should be clear, that you can describe every vector which is rotating around this point on this circle. You can describe every point not just by vectors, but you can also use complex numbers. So y can be thought as a complex number which is rotating around this circle. And the most profound property of complex numbers, or the most important, is that if you have complex numbers z1 and z2 in a grand plane, or the Gauss's plane, and you multiply them, then the result is another complex number with the magnitude, or the length from the center, equal the product of those two magnitudes, these two distances, and the angle from x-axis or from real axis is exactly sum of angles of these two. This is a very important property, and this enables us to write velocity which is perpendicular. This is perpendicular vector, and I can write this as perpendicular to y, to number y, complex number y, as this point, as I times omega times y. When I take the magnitude, you will see that v is r times omega, because r is magnitude of y. So this is from high school, a very easy formula. Y is v velocity is that, and acceleration is that, but with the minus sign when written with y as a complex number. These two equations are very important, and I will return to them later. What next? First, I will analyze motion of a spring with just these two forces. When these two forces, I will write the second law of Newton, second law of motion, which says that the sum of all forces is equal to mass times acceleration of this body. What is sum of all forces? The sum is mg in this down direction are positive forces, and this is direction of x and y. This is direction of x and y. This direction is mg minus k times x0 plus y, and this is equal to m times acceleration. These two terms cancels out because they are the spring is in equilibrium, and when they are in equilibrium, y is 0, a is 0, so this should cancel out. This should cancel out. So that means that the equation of motion I am going to solve is this. Let us assume that the motion is periodic and harmonic, so it can be viewed as a projection of taking a real part of rotation of complex number around this with angular velocity omega. This equation holds in R, so the plan is I have some problem and add to the one problem the second problem. I will solve these two problems, and then I will forget the second one and I have the answer of the first one. Adding the second problem means that let us suppose that this equation holds in R, and I will then add just one equation in imaginary parts. So this equation is now in C. When this equation is in C, in complex numbers, then complex acceleration is given by minus omega squared y. Why? Because it's this vector is minus this vector. Yes, Utah's vector on 2D. So this is minus k y, and this is equal to minus m times omega squared y, and then I will get these two cancels. So, and I will get that omega is equal to square root of k divided by n, which is exactly angular velocity of moving spring. This I will write there index 0, subindex 0, and I will refer that as natural frequency of moving spring. So this is natural frequency of moving spring. So now we are fully prepared to tackle the problem of moving spring with damping first, and then I will show you how to derive the resonance curve. So what I'm going to compute now, I will add to our problem. I have this spring with a spring constant k, and there is this bob with mass m, and there is force mg, and the second force of spring is k times x0 plus y, where y is the displacement from equilibrium position. And I will add another force, and this force I will refer to that as like damping force. Yes, damping is due to velocity. You can thought it is a friction force, and it's I will write it as it's some multiple of velocity, and it's the opposite direction of motion, which is assumed to be in this downward direction. Positive motion is in the down direction. So let us write the constant of before this v as 2 times delta times m. Delta can be any real number, so this is any real number. So for some reason I will write this as this constant of this friction force. So what next? I will just now write the second law of Newton, or second law of motion, which states that all forces are m times acceleration, mass times acceleration, which means that mg minus k times x0 plus y minus 2 delta mv is m times acceleration. Let's assume the motion is harmonic, which isn't, because when the spring is damped due to friction, the motion should eventually stop. but let us assume that the motion really is harmonic, and we are able to express all the constants as a projection of complex motion. So that means that I will cancel these two out as they should, because in the equilibrium at the end of all of time these are 0, so this should be 0. So we have this equation minus ky minus 2 delta mv is equal to m times acceleration. Then I will substitute our equations for v and acceleration, for velocity and acceleration, and we will get minus ky minus 2 delta m I omega y is equal to minus m omega squared y. This will cancel out, so there is no need for coming back to real problem. Yes, coming back to real problem, no need for that. Now I will cancel m. I will divide by m, so this should cancel, and there is a mass over there which I can write as omega 0 squared minus 2 delta I omega is equal to minus omega squared. I will put this omega squared to the left side, and I will get just quadratic equation which is solvable very easily, so there is no problem with that. So omega is, after simplification, it's plus minus omega 0 squared minus delta squared. What does it mean? What does it mean this? To have this omega. Here omega is complex number. What does it mean to have an angular velocity as a complex number? So let us write. I will show addendum or a bonus in this video, which explains why this makes sense and how does it make sense. It's not so complicated to show that this will lead to exponential decay, which we are supposing that this is the solution of the damped oscillator indeed. Because when you have, let us assume that you have some point in complex numbers which is rotating with angular velocity omega, and the point is t, and in the next time this should be t plus delta t. Yes, it's in the next time. This vector is in the limit perpendicular to this vector, and it's not easy to see that this I should call delta y, that this point t plus delta t, this position or this vector is just t plus velocity delta t. This is just regular mechanics, yes. And v is what? V is from the previous chapters, v is plus I omega y t delta t. So that means that t plus delta t is equal to t and 1 plus I omega delta t. That means that every addition of delta t, delta time, the current position is multiplied by this complex number. Let's divide the time from time 0, when the position is in some y0 position, to position at just some t in n pieces and very small intervals, and delta t is just t over n. I will count from 0. So that means that yt should be written as y0 times 1 plus I omega delta t to the nth power, because it's multiplied n times. that means that it should be written as y0 1 plus I omega t divided by n to the power n. And many of you will notice that this is very similar to this 1 plus x divided by n, 1 divided by n over n, because in the limit this will approach the Euler's number when n is infinity, and when there is x, this is just complex exponential. So this should be thought as some exponential, and where x is equal to y times omega times t. So this is y times omega times t. This can be viewed as this. So this can be viewed as rotation of some point in complex numbers. If you compare this with the expression of pure rotation with cosine, if you using cosines and sines, you will get famous Euler result that exponential of I times something is cosine of something plus I times this something. Yes, so this result. But this is not the goal of this video, so I will skip everything. I will skip this and I will continue in our problem. And first, let us note that I will use this just for a moment, because when I have this formula, which is over there, I can substitute in our result of complex angular velocity, which is over there. So when I substitute in, I will get the actual motion. So this is y t is equal to y0 times e times delta I plus, I will just use plus, but never mind, square root of omega 0 minus delta square times t, which can be simplified as y0 e to minus delta t times e to the power of I times square root of omega squared minus delta square t. This can be viewed, this part, as again rotation, and when you can make rotation in complex numbers, and when you make projection, this is just cosine function. So it will look like cosine function, but because there is this term which is damped exponential, so this will eventually decay to zero, so it looks like this. So this is real function or real solution of this. Okay, let us take us back to our original problem, which is to derive the resonance curve. What is the resonance curve? Imagine that you have a spring which is attached on this, and at the end of the spring is attached some mass, some bob with mass m, and with mass m, and there is constant k, and the spring is pulling on the bob with the force k x0 plus y, which is the same as in the previous cases, and there is gravitational force which will cancel out with this k x0 force, and there is another force which is the friction, which is 2 delta m v, just the first power of v there is, and then I will add some force which is pulling on this mass, but just some force F. This force is time dependent. And let us assume that I am pulling on this bob like a cosine function, yes, up and down. So it's like pulling on a child on a swing, yes, and it's moving up and down, and you are trying to move it as fast or as far as possible. And what should be the frequency of the force? So the amplitude of moving bob should be at the farthest point. So the question is to find amplitude as a dependent function on omega. When you are studying this kind of problem, the second question will arise, and the second question is this. First, you have to accept the lemma that the actual angular frequency of motion of this bob is the same as the frequency of the force which I am acting on. So let us just draw cosine as there is some maximal force F, and this is the function which describes in sometimes what looks the force, and the result or the actual motion of bob can be not just multiplied but also translated. But the period is the same. Should stay the same in the limit. Should stay the same. So it can look like this. So there can be some shift, and really there is some shift, and the shift is dependent. The shift is dependent also on omega. So the question is how to find these two functions. Again, you can, this is the amplitude of this motion. This is y and this is f. Again, you can thought this motion as a projection of complex rotation in complex plane. There is some point at the edge of the circle moving in the frequency omega, and there is another point which is moving with the same frequency. This is the thing you have to accept for solving the problem. This is f point, this is y point, rotating again in the frequency capital omega. So when they are moving with and this angle is the shift in it's called a phase shift. Yes, the phase shift, and this is the amplitude. And how to find this? Again, let us recall our property of complex numbers. When, yes, they are rotating, so this point can be here, but this is here, and the distance from the center is not changing, neither this distance. So there should exist some complex number. I will call that complex number capital lambda. Yes, so this is y is capital gamma times f. This complex number, which can just multiply this f and you will get y. From reasons of measurements, this is in meters. Yeah, this is displacement. So what is dimension of gamma is force, meters divided by force, and I will divide here. So this is there's no this has no unit, so this has just meters. So then from this equation, it's easy to write that A is the magnitude, complex magnitude of this complex number, and phase is argument of this complex number. Let us write the equation of motion. The equation of motion is the equation of motion from this picture. From this picture should be minus. This will cancel out, so I will skip that part. So it's minus ky minus 2 delta mv plus, in this direction is pulling that force, plus f, and this is mass times acceleration on the other side. When you substitute in the velocity, which is I times omega y and you substitute in a, which is minus omega y, and you substitute in f as this, you can derive the expression for gamma as follows: gamma as minus f divided by m divided by omega squared minus omega 0 squared minus 2 delta I omega. And from this is straightforward to find that amplitude function is this value magnitude is square root of omega, capital Omega, this is squared plus 4 delta squared square, and the phase is argument of gamma, which is going to be arcus tangent of 2 delta lambda divided by omega, capital Omega minus omega 0. These two functions, how does they look like? They look like something like this. This is the resonance curve. This is the resonance curve. The resonance, the maximum is not in omega 0. The maximum is not in omega 0, but rather in square root of omega 0 squared minus 2 delta square. And the curve which describes the phase, it looks like this, and there is pi exactly in omega 0. Oh, I'm sorry, this is like this omega 0 over there is omega 0, and there is 2 pi. This is the curve of phase curve with respect to capital Omega. So this is A and this is phi 0. So for delta is equal to 0, so there is no friction. This looks like there is singularity, and this is 0 exactly. So there is no phase, so there is no friction. So I hope you enjoyed this video, and I hope vectors and complex numbers will be helpful in your analysis in the future.